Okay, so last time we showed how Newton's laws were invariant under the Galilean transformations. Now we're going to see if how they apply to electromagnetism. Okay, so last time we went through these Galilean transformations, and we said that the laws of classical mechanics, which are Newton's laws, are invariant under the Galilean transformation. That meant that F equals ma in one frame. When you transfer it to the primes, it's F prime equals ma prime, which meant that we have an infinite number of coordinate systems that would apply to Newton's laws right here, as long as they're moving at constant velocity right here, which meant it was impossible to detect absolute motion right here. All you can do is say your motion is relative to someone else's. Now, we didn't bring it up but it's also true even for Newton's law of gravity. If we look at Newton's law of gravity right here, we'll just, remember it's gm m1 m2 over the distance squared. Well, if we just say the distance is between two x positions in Frank's frame, you just say x2 minus x1 squared. If we convert this to Mary's frame, we already know that's an absolute. These two were absolute, so it's still the same. If we just look at this bottom part, x2 prime minus x1 prime, if we just apply this rule up here to turn it to unprimes, we get x2 minus vt2 minus x1 minus vt1. But I'm assuming when we measure these two positions, we're doing it at the same time. So T1 and T2 were equal, so those two just drop right out, and we're left with x2 minus x1. So Newton's law of gravity is also invariant under the Galilean transformation. So all of Newton's laws are invariant right here. But now I want to look at electromagnetism. You notice when we learned electromagnetism, we didn't dwell on forces in electromagnetism. We actually dwelled on fields right here. And why did we dwell on fields? Well, because, when you look at gravity even, right here, we use fields even for gravity. You noticed here, we have the sun here, and we have the earth here, and you say, how the heck can the earth apply a force? How can there be a force on the earth due to the sun when there's nothing in between right here? So the way we interpret it is, we say, well, the sun puts out some sort of a field right here. And then he senses that field, and that's what gives him the force right there. So it's because we have action at a distance right here. When we had something like normal force, your hand against the wall, there is still action at a distance. Your atoms don't really touch these atoms, but the distance is so small we don't even notice it right here. So later on, everything is a field right here. Okay, well, let's look at, for fields, let's look at gravity first right here. So what did we say? We said if we have some mass, let's say big M right here, this mass, this property of mass, sends out this field. We call it a gravitational field right here. And so if we wanted to know what the field was at some distance, say R out, right here, if we want to know what is the gravitational field there, well, let me see, what should I call it? I can't call it little g, because little g is only the field near the surface of the earth, so maybe I'll just call it fancy g. Fancy g, right here. The field, the gravitational field right there is related to big G, gravitational constant, the mass, and r squared, right here, the magnitude of r squared. Okay, it's r squared because we live in 3 dimensions of space, and when you spread out in 3 dimensions, you drop off as a 1 over r squared right here in intensity. Okay, so there's the field. Now, if we put an object out here, say another mass right there, some m prime right here, we put out here's some m prime, then it senses there's a force on it right here. He doesn't feel his own gravitational field, but he feels this one right here, and we say F is equal to, the force on this is equal to m prime g. Just like on the surface of the Earth, it's m little g right there. Okay. And since this is an attractive force, we say that since this is an attractive force, since we're going to call R out this way positive, the force is actually this way. So this is a negative, and it's actually because of the G. The gravitational field is negative right there. So if I make that a vector, it looks like this. I guess we could even put it like that right there. It's in the R direction. This like this and like that right here. Okay, so there it is for gravity. If we plug this in, we end up with Newton's law of gravity, which is G, big M, little m prime, all over R squared. It's negative, it's attractive in the R direction. Right here. Okay, so there's Newton's law of gravity right there. Okay, but when you take electromagnetism, you notice that there is another property of particles that gives off a completely different field right here. And we don't call that property mass, we actually call it charge right here. So here, and we don't want to use C for charge because we use C for too many other things. We'll use Q right here, and that's charge. And that puts out a completely different field. And out here, some distance R, we get a different field. We call this an electric field right here. And we say the electric field out there is given by a different constant, K, times Q all over R squared. Looks a lot like this one right here, GM over R squared. Okay, now if we put another charge out there, so if we come out here and we put some little q prime, then it feels a force, F, just like we did over on this side right here. And we say F is equal to q prime E. There's the electric field right there. And then if we plug this, oops, sorry, I didn't want to make this a vector yet. If we plug this into there, we get the force, which is K, Q1, Q2, all over, sorry, big Q, Q prime, all over R squared. We call that Coulomb's law right there. Now, you might say it looks exactly the same as this. Two differences right here. One is the strength of the force. This K right here is a lot bigger than this G right here. You know, if you look at hydrogen, which is just a proton and an electron going around it, if you compare this gravitational force with the electric force, this one over here is infinitely larger. Comparing these two is like comparing a grain of sand and the earth right here. Matter of fact, when you take electromagnetism, you ignore gravity because it is infinitely weak right here. Okay, and that's one. Now, if this is infinitely stronger than that, why don't we notice it? Is because charge comes in two flavors right here. We give them positive and negative, plus and minus right there. And if this thing is positive, then the field goes outward. So this is in the R direction, and this is E right here. If charge is negative, it's in the minus R direction. So, and then when we come back to here, if this is positive, then these two are in the same direction, and if these are negative, these two are in opposite directions, which means that unlike charges attract, like charges repel right here. Okay. So, other than that, they look almost identical right there. Okay. Now, except in electromagnetism, we had another field. We actually said we have something called a magnetic field. And where do we get that from? You get that from just moving this charge right here. So if we just take our Q and we move it this way with a speed U, right there. Then we get a magnetic field, say right there, some distance r away. Now we don't want to use M for magnetic field. We use actually B for magnetic field. We use B right here. Now, what is B right here? Well, they usually give you Biot-Savar's law. I'm going to write it a little differently. It's actually just KQ all over R squared times U cross R hat all over C squared. Now you might say, well, that didn't look like the one I had in 4B right here. I think you will probably remember something that looks like mu naught over 4 pi, and QV cross R hat right here. But let's look at the mu naught over 4 pi. You notice mu naught epsilon naught we said was 1 over C squared, and K is equal to 1 over 4 pi epsilon naught. So you can see right here, if I take mu naught and I divide both sides by, so now if I go mu naught over 4 pi, well, mu naught is 1 over epsilon naught C squared, 1 over epsilon naught C squared, and then we also have a 4 pi here, 4 pi. Now, K is 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught, so this is just K over C squared. Okay, so that's where I got the K over the C squared here. Okay, so I just wanted to write it like this so that it looks the same right there. So that gives me the B right here. So if I wanted to know the B right there, if this is a positive charge, U is going that way, R hat is going this way, the B would be coming out right there. Okay. And then if I put a moving charge, I have to have a moving, whatever is here has to be there. It couples to itself, just like whatever's here was there. We get a force. If there's a moving charge, I don't know, maybe I'll call that one going this way at some speed, U prime. It's not in Mary's frame, it's just some other speed right there. Okay, and we can say the force, and this is some Q prime. We can say the force is equal to Q prime U prime cross B. Probably right there. Okay, and then if I plug this into here, into my B right there, we end up with K equals K, Q, Q prime all over R squared. And then I'm left with U prime cross U cross R hat all over C squared. Okay, so that's really the force between two moving charges. It depends on the two velocities right here. This was the U prime, this was the U right there. Okay, so first of all, you can see once we start to get a velocity in here, I don't see how Frank and Mary are going to agree on. They don't agree on velocity. How can they possibly agree on force right here? Matter of fact, let's say we have Frank's frame here. Here's Frank. And let's put two charges here, one here and one there, a distance y apart. Let's just make them Q and Q, and they're both at rest. If they're both at rest, we don't even have to worry about this. There's no movement. We do have this force right here. And we'll nail this one down. We won't nail that one down, so that one will take off. But the force on it, the force, and this is in Frank's frame, because this is all X and T, X and Y, sorry. This force would be K, Q, sorry, both Q's are equal, so it'd just be little q squared all over their separation, which is y squared. This is what the force would be right there. This is in Frank's frame. Frank. Now, if we look at Mary's frame, with Mary's frame, what does Mary see? Mary sees these two charges moving to the left right here. She sees this charge moving with this way and this moving both with the speed v, because she's relative to Frank, she was moving that way. So we got these two charges moving this way with the speed v. Well, we still have, so on Mary's, we still have an electric force. That still stays the same. So you still have F equals KQ squared over Y squared. Remember, they agree on the Y right here. Y prime equals Y. But there's also a magnetic force right here because we have both of these two moving. So this is the electric, but the magnetic force, we would get all of this, KQ squared over Y squared, except we get this term right here. Now, what does this give me? First of all, what is U cross R hat? Well, that's this cross R hat. So it's this, and R hat is up. That's into the board. So this, the direction of this is into the board. That's just this part right here. And then we're going this, that's the other, the U prime cross in is going in that direction. So the directions of all of this is just down. And we get both the speeds would just be v squared. That has, remember, a magnitude of 1. So we just get v squared over c squared. And it's down, so it's a minus right here. So the total force in Mary's frame, it would be KQ squared over Y squared. And then it's just sum of these switches, that's a negative, 1 minus V squared over C squared. So Mary says that's the force. Frank says this is the force. They definitely don't agree. According to over here, both forces, F equals F prime, right here. Well, if F doesn't equal F prime, both of these two coordinate systems can't work right here. Only one can give me the right answer. So it looks like for electromagnetism, there's only one good frame right here. So from right here, electromagnetism, there's only one good frame. Good frame. That's kind of strange because for classical mechanics, we have an infinite number of frames. For electromagnetism, there only seems to be one good frame. So how do we determine who's got the good frame right here, and why is there only one good frame? Well, it's not that hard to see because you notice when we deal with sound, sound has a special frame too. It's still air. That is, if you have a speaker here and your ear is here, here's your ear. If your ear is moving toward the speaker, that's different. You get a different equation than if the speaker was coming at you. Remember, with relativity, you shouldn't be able to tell the difference, but with sound, we can tell the difference between these two. Why? Because there's a special frame with sound. It's the speed of still air right here. You notice if you ran toward it right here, you would get a speed faster than the speed of sound. Over here, if this speaker is coming at you, you still get the speed of sound. It's just a higher note right here. So there is a special frame when there's a wave. Well, there's a wave over here, electromagnetic wave right here. So that special frame must be relative to, well, this was still air, maybe still space right here. Maybe that's the good frame, still space. We don't know where that frame is right here. We'll have to try to find it right here, but so there's only one good coordinate system for electromagnetism right here, and it's the frame of, we're going to call it still space right here. Now, how come we haven't seen it before? Why can't we just measure this? And not only that, it's not just force, I should say. You notice, if both of these two were released, and let's say we had a plate up here, since the force is bigger for Frank, because this one is deducted a little bit, wouldn't Frank say that this particle got up to here a little bit quicker than Mary would say? And so they wouldn't even agree on the time it took to get there right here. So there's a lot of things that they won't agree on. So there's really just one frame that works right here. So we have to figure out what that frame is right there. Now, it's not easy to find right here because you notice you got this v squared over c squared term in here. If you look at our motion around the sun, the Earth going around, here's the sun over here, we go around the sun, we're going about 64,000 miles an hour. That's about 3 times 10 to the 4th meters per second, 64,000 miles an hour. Now you might say, okay, then how much does this equation differ by, just by us going around the sun right here? Well, it's going to drop by this v squared over c squared. Well, v squared would be 9 times 10 to the 8th, and c squared would be 9 times 10 to the 16th. So this ratio is like 10 to the minus 8. So this, just us moving around, would deviate it by 0.0, 2, 3, 4, 5, 6, 7. Would deviate it by this amount right here. You're not going to see this. This is just unmeasurable right here. But so it's going to be very difficult to see this deviation right here. But we want to find out where this special frame is, or at least how fast the Earth's going through this frame right here. A lot of people thought it might be impossible right here, but in the next lecture, we'll show that one guy, an American named Michelson, figured this, how to measure this, the speed of the Earth through this still space right here, measuring things this accurate right here, which is in one of the most classic experiments in all of physics. I'd say it's one of the top 5 experiments in all of physics right here. Most profound right here. And he was the first American to win the Nobel Prize for it. I think he got it in 1907 right there. So we'll go through that next time. And so just to remind you that there's only one good frame for electromagnetism, but we have an infinite number of frames for classical mechanics. And one last thing is, usually we deal with Maxwell's equations when we're dealing with electromagnetism. I might just, well, we'll do that in the next time, deal with Maxwell's equations. Okay, and just to remind you, there's only one good frame here, infinite number of frames in classical mechanics. Okay.